always tough to follow Andy. It's always kind of exciting. So how many people have heard about RSD? Okay, a few of you have heard about that. How many have heard about SPDK? That was a trick question. Hopefully everybody's heard about it today. So what I'd like to talk about is a storage system we put together that actually utilized SPDK and why we chose it and what it does and that. But before I get into that, what I wanted to do is give a little bit of background on the program that we were working on that led to us developing the storage system, and then talk about the features and the requirements that we wanted to achieve, and then how we used SPDK to implement them. So RSD is a set of standards that was been developed over the last 4 or 5 years that was really intended to build a better data center, to build a more efficient data center. And the core fundamental of rack scale is to be able to disaggregate resources and compose them back together. And when you think about how resources are consumed, particularly where you have various different applications running and different applications need different amounts of resources, whether it be storage or accelerator, having fixed resources in servers makes it more difficult and less efficient to schedule the use of those resources, because you may have some free cores but not enough, or some free memory but not enough, or you may need more or less capacity of storage, or you may need a whole accelerator or multiple accelerators, and you may not have a server that has the amount of free resources that you need, where if you can compose them, you can compose what you need more easily. So when we think about building a data center that's agile, and you want to build it on open standards, we really want to take these fixed assets and make them composable so you can use what you need when you need to use them. So a way to think about it is, instead of having all your compute and storage and accelerators evenly spread out across the servers, the idea would be to have them separated and connected with a very high performance network that allows you to then take and compose where you might need a server with a lot of storage, maybe a server with less storage but a number of accelerators, and how would you put that together? And that was the crux of building the rack scale system. And you can see that we have many different vendors that are building rack scale compliant hardware, and they are all interoperable by a single management layer. And the value proposition for being able to do that is really being able to create a resource pool that's more efficient. The example I'd like to talk about is, you can imagine that you have a server that has a single SSD in every server, and you have maybe 30 servers in a rack, so that's 30 SSDs. And each one of the servers may need, for short periods of time, the performance of that SSD, but the bulk of the time they don't use that performance. It sits idle because the server's busy doing work. But you can't not have the SSD or the performance of the SSD, but you're not fully utilizing it. So if you could disaggregate that SSD from the server, along with all the ones in the rack, and create a pool down in the bottom, you can provision back up a logical volume that, if the network's fast enough, can deliver you the bandwidth instantaneously that you need. But you don't have to have 30 SSDs in the bottom of the rack. You may be able to have 10, maybe even 5. So you can save a fair amount of dollars, both in the pooling for capacity as well as performance. You can refresh modularly, so you don't have to refresh everything at once. So you may be really happy with the SSDs you have. You may be happy with the accelerators. You may just want some faster CPUs, or vice versa. The more modular system allows you to do functional upgrades of classes of things that you want. And of course, it will lower your operation costs because your pool is more efficient. So, and this shows that all of this is managed with orchestration software that allows you to compose nodes and be efficient. And we're going to talk really on this guy here, on what we did to create a disaggregated, composable storage sled, and how we used SPDK to achieve that. So, storage disaggregation. In a lot of ways, this has been done for years, right? SANs have traditionally done this. They typically use fiber channel or other proprietary interconnects. We wanted to base the disaggregation around Ethernet. We wanted to be able to deliver as close to locally attached SSDs performance as we could, which meant that we wanted not only a very high performance network, in this case we used 100 gig Ethernet, but we also wanted to use something that didn't consume a lot of CPU, because we didn't want to have a lot of resources being spent on that. And as you heard earlier in Jim's keynote, the RDMA SPDK is quite performant. We'll talk a little bit about some of the performance later, but we chose RDMA. And we wanted to deliver a set of features, and the features that were important for us, as I said before, high performance and low latency. So we want to have performance on a logical volume that makes it look like there's a locally attached SSD. But we actually wanted to go beyond that. And in some cases, there are applications that want more than a single SSD's performance. And so some servers today will have multiple SSDs in order to do that, which just makes your efficiency worse if you had to do that. So we support RAID 0, which is striping. So not only can we provision up a logical volume, we can create that from multiple SSDs. So in the network that we have today, it's 100 gigabits a second, roughly 10 gigabytes per second. We can take 4 SSDs and we can actually get the performance of 4 SSDs, but in a single volume, a single logical volume. The striping gives us that. We support cloning. Thin provisioning. Thin provisioning is, again, a very valuable tool in being able to say, well, you may have asked for 100 gigabytes, but you may only have 10 gigabytes of data. So I'll tell you, you have a logical volume with 100 gigabytes, but I only have to have 10 gigabytes of space. Now that's not really that important when you only have one thinly provisioned volume, but if you have 1,000, then not everyone's going to grow simultaneously. So you can have a lot less storage and still deliver that same capability. Snapshots, quality service. This is the one feature that is in the software that I'm talking about here, the CBS software. That's not in the current SPDK release. This is something that we developed as part of this program. It will eventually get into the release tree, the open source release tree. I just can't tell you when because it's still being developed. And then, a couple of bullet points, right? Obviously, SPDK. We wanted to be very efficient in the use of our resources, and we wanted to have standards-based management. So that was kind of the requirements of what we were going to go do. And we looked at, well, should we do something in the Linux kernel? Should we write it from the ground up? How are we going to achieve all of that? Kind of giving the story away a little bit, because we chose SPDK, and a lot of the features that we wanted, you can see were already in SPDK. The user space capability in SPDK was really nice. It allowed us to write code and test it in a much more thorough way than what you might do if you were trying to run in a kernel environment. So, as you can see here, we leveraged the BDEV abstraction. In fact, you'll see us in future talks down the road adding more capabilities into this. Was one of the reasons why we wanted to use it. Again, I talked a little bit about the user space app. That was really important for us to be able to deliver it. And of course, the async capabilities allows us to get very low latency and very high performance. A couple more key features in SPDK. Lockless architecture. that's really key. You know, storage is one of those problems. If you've ever developed any large storage problems, it's an embarrassingly parallel problem, to which when we start off writing a storage solution, we put a big lock over the whole thing. And there's many cases where that's where it started. I think Seth started a lot like that with locks over major portions of the code. Every time you do that, it really impacts your performance. So we wanted to start with something that's lockless, that gives us a framework for that. We wanted to be able to have core affinity. One of the other challenges as we look at architectures going forward, if we can have system affinity, meaning we have a network card, we have SSDs, we have them on the same socket, we can direct affinity to them rather than having to go across UPI connections to the other side, although we don't need to. That's going to drive efficiency. We're creating pools of storage. We want them to be efficient. So core affinity really helps with that, helps to deal with some of the end-to-end things. And of course, we wanted to have exceptional error handling. One of the key points in trying to develop this was, and if you do develop storage solutions, you probably know this, customers, when you have some anomaly, and it's not a matter of if you have an anomaly, but when, they'll ask you two questions. They'll ask you, why did this happen? Why did this anomaly happen? And what did you do to make sure it doesn't happen again? And without really good telemetry and error handling, those are two very hard questions to answer. So that was something that we started at the get-go that we wanted to have in the beginning. So the name of this is called CBS, which is Composable Block Storage. It's built to be disaggregated storage for big data centers, where we can deliver local attached SSD performance at over the network. So they were talking. Jim was talking today. He was getting about 10 million cores or 10 million IOPS with one core. I said a few cores in here, just to be a little bit safe, because when we were working on this, I think he was still trying to get to 10 million. We wanted to be able to use Optane SSDs. One of the advantages that we see in this technology is you can actually get higher performance to your servers by saying, I'm going to pool Optane SSDs. And the pooling is going to save me money because I'm buying less Optane drives than putting one in every server. And so for maybe a little bit more than what an individual NAND drive would be in every server, I could run a pool of Optanes. And of course, as you know, a pool of Optanes will give you 10 microsecond access versus 100. The network's maybe 5 to 10. So you can get 20 microsecond access for a little more than what the price of 100 microsecond access would be. So that's another thing that you can actually do with this. Let's jump to a little bit of configuration. So I'm going to talk about some performance that we did. And you can see this is our SPDK VDEV system for the target. We used Wolfpack server with a few SSDs in it, 8 SSDs. You can see it's Fedora, SPDK, OFEC, and the like. And here's some rough numbers of what we were running. Synthetic workloads, 4K random, 128K sequential, Q depth of 1 to get kind of the latency numbers. And you can see that 3.14 million IOPS, that's pretty much us 100 gig network, totally saturated. The writes, it wasn't network saturated, it's more the drives get saturated because there's only 8 drives down on the end of it. You can see the mix of read writes. Again, I think you're getting saturated in the drive. And when you get to sequential, you're again network saturated on that. 12.5 gigabytes per second is 100 gig, pretty much. So if we look at some of the performance curves that we have here. This is showing, this is a single drive, and in both cases, single drive. One is with the RAID 0. This is 2 drives with RAID 0, 4 drives with RAID 0. You can pretty much see that a single logical volume bumps up and increases as I add more drives, up until, you know, when I get 6 and 8 drives, you know, at that point I start pumping into the network. And you can kind of see the same thing is true for write. So 2 takeaways. First of all, doing the RAID 0 has effectively 0 impact negatively, in that when I have a RAID 0 RAID group of 1 drive, it's the same as just 1 drive. So there's very efficient overhead in that. I'll go through a couple more. Pool configuration performance. This, you know, as the queue depth scales, you start to see performance. Obviously, with small queue depths, right, you struggle with performance until you can get enough stuff queued in. But again, you can kind of see the OneDrive pooled to the OneDrive not pooled is virtually identical. And then as 2 and 4, and then you pretty much hit the network saturation. And here we look at write. Some interesting anomalies a little close to the end we're still looking at. But again, for the most part, you see that the pooling increases pretty linearly as I add more drives. And here we have, again, the read IOPS as you scale out. We're all going to look pretty close to the same. This is the latency. Obviously, when you have you know, a pool, you wind up with getting here with the queue depth of 3072. There's a fair amount of latency just because you have to fill up the queue. And then as you add more volumes to it, that latency goes down because you can drain the queue and address it that much quicker. Right? It's that much more bandwidth that applies to it. The last one I have here on performance is random write IOPS to a single SSD versus a pool. And you can see here we are still working on optimizing some of the writes. This would be a great opportunity to employ write caches in PMDK, as you know, Andy was talking about before. So I'll leave you with a little bit of a teaser that perhaps next year I'll be talking about how we use PMDK for some things. And with that, I'd like to open it up to questions.
What's the difference of a single NVMe drive and pooled volume with the one? The configuration difference?
So from it's the way we configure the software. The reason I show those two is to show that the impact of pooling, of the RAID 0 pooling, is very minimal. Sometimes you will have overheads that are involved in creating a pool with multiple devices, even if you only put one device in it. And what I'm trying to show here is that the pooling into a RAID 0 is very low overhead.
Hello, I see you also use the NVMe fabric, RDMA, and SPDK host and SPDK target. And actually, we are trying developing our product with these two, but we found there is a serious RDMA flash I/O. So currently, we lack the debug methodology. So do you have any idea or insight you can share to us how to debug this kind of RDMA I/O? Flash I/O.
Okay. So what we did was use a Linux initiator with an SPDK target. We weren't using the SPDK initiator for the reasons of these tests. The load was generated with 2 FIO. And so we weren't really seeing much of a performance gap in either read or write with FIO. Were you using something like FIO to generate load, or did you have something else?
We actually are a distributed storage, so we will have in-cast scenario.
Oh, okay, in-cast.
Yeah,
Okay, yeah, okay.
Play that.
On a little bit different note, right? We have, in order to make this work, we kind of have to solve the quality of service problem. And I talked a little bit about some of the quality of service features. We're also in the process of building out a 512 node cluster because we're trying to extend beyond a single switch, right? So a single switch is interesting, but you can pretty much make a single switch and the in-cast problem work with DC QCN, right? If you do that, that's pretty straightforward. And a single switch is fast enough that you can react to that. But when you go beyond a single switch and go to like a 2-tier or 3-tier network, that's where the problems really start to come. So I built a 500 node cluster. It's a full factory, 100 gig, and it's all Columbiaville. And we're just now starting to go through and try to find out where the limits are around that particular, how do we manage the quality of service. Also, I've got a team that just joined my team that came from OmniPath, which was our HPC interconnect, and they built a simulator, fabric simulator for OmniPath, right, for the HPC. We've taken that simulator and we've retooled it to simulate Rocky V2, iWarp, and just regular TCP. We're going to correlate that simulator with the 500 node cluster. And that simulator should be able to take us to tens of thousands of nodes. So we're going to try to develop a set of best practices from a few hundred nodes to a few tens of thousands of nodes for RDMA at scale. That's one of the goals. I didn't really talk much about that, but you're absolutely right. The in-cast problem is a big one, and how do you manage the end-to-end flow control to avoid that? So I don't have an answer for you yet. Probably mid-next year, I hope to have an answer, but we understand this problem. There's a couple of papers by a couple of different companies that you've probably read already. With our recent acquisition of Barefoot, the cluster that I have is all Arista switches. We're also going to be adding Barefoot switches into the cluster, and so we'll be able to come up with solutions for both of those.